You're listening to AI Podcast. I'm Daniel, and today we're unpacking a paper called Graph of Thoughts: Solving Elaborate Problems with Large Language Models. Quick takeaway first. Instead of forcing an AI to reason in a straight line or even a branching tree, the authors guide it through a flexible graph of intermediate ideas. That shift lets the model split a problem, try options in parallel, merge partial answers, and loop to refine them. In controlled tasks, this approach beat earlier prompting methods on accuracy and often on cost, especially compared to tree-based prompting.
I like that you started with the bottom line. So, a graph instead of a chain or a tree. Before we go deeper, who's behind this?
The work is led by Maciej Besta at ETH Zurich, with Torsten Hofler as a senior author, also at ETH. They collaborated with engineers from Klidar in Poland and a contributor from Warsaw University of Technology. It's a solid mix of academic and industry perspectives.
Got it. To set the stage, what problem were they walking into? What's hard about prompting models for reasoning?
The field moved from plain input-output prompts to chain of thought, which asks the model to think step by step. That helped, but it's still one path. Self-consistency samples multiple chains and votes, better but still linear. Tree of Thoughts explores branches with backtracking, which is a step forward. The catch is structural. A tree splits, but it doesn't naturally merge branches or add feedback loops between them. Real problem-solving often needs exactly that.
So the gap is that a tree can't easily bring ideas back together or run repair loops. That's where the graph comes in?
Exactly. They treat intermediate thoughts as nodes in a directed graph and dependencies as edges. With that setup, they can plan 3 operations inside a single reasoning flow: generate candidates, aggregate partial results, and refine by looping to improve what's already there.
That sounds elegant. How did they know it would actually help? What's the core intuition?
Their hypothesis is that many tasks get easier if you decompose them into sub-problems, solve those locally, and then combine the pieces with the option to clean up mistakes. A graph makes that decomposition explicit. They also introduce the idea of the volume of a thought, which is a way to talk about how many upstream ideas can influence the final answer. Graphs allow a larger useful influence without forcing everything through a single bottleneck.
I like that image. How did they test the idea?
They ran controlled tasks where scoring is clear: sorting lists of digits, set intersection, keyword counting in text, and a more open-ended task, merging several short legal documents into one consolidated draft. For each task, they designed a small graph of operations, split the problem, solve subparts, merge results, and run a brief repair loop if needed.
And what did they compare against?
They compared to input-output prompting, chain of thought, self-consistency, and 2 common tree of thoughts setups. They kept evaluation budgets comparable by controlling how many samples or thoughts were generated. Most experiments used a GPT 3.5 class model with a standard sampling temperature. They used roughly 100 inputs per structured task, and about half that for the document merging test, with context lengths adjusted to fit the task.
That sounds reasonable. So did the graph actually make a difference?
It did. On sorting, the graph approach cut errors substantially compared with the tree method and did so in a representative setup while also lowering inference cost. On set intersection and keyword counting, it generally outperformed the baselines at a similar or better cost profile than the tree approach. And in document merging, where you aim to retain important clauses without redundancy, the graph strategy delivered a better balance under their scoring rubric.
Nice. What's their explanation for why it works?
Divide, solve, merge. Many mistakes happen when a model tries to juggle too much at once. If you split the problem into digestible pieces, the model is less likely to slip. Aggregation then gives you a chance to cross-check and repair. The volume idea helps explain the benefit. The graph lets more useful intermediate work influence the final answer without a single narrow path.
How heavy is this in practice? Are we talking about complicated tooling or careful prompting with a bit of structure?
It's structured but manageable. There's a controller that tracks the plan, the graph of operations, and a dynamic record of what's been generated. A prompter formats requests, a parser turns outputs into structured thoughts, and a simple scoring component helps choose among candidates. Think of it as light scaffolding around the model, not a full-blown agent. The trade-off is that someone needs to design the graph for each task.
Right, so there's human design effort. Any other caveats we should keep in mind?
A few. The benchmarks are structured and controlled, so it's still an open question how the method fares on messy, open-domain problems. Most results are on a GPT-3.5 class model, and they reported limited tests with an open model where quality and speed lagged in their setup. For the document task, they used an LLM-based evaluator to judge retention and redundancy, which is practical but can add variance. And while the graph can be more cost-effective than tree search, it still means more calls than a single pass or a simple chain.
Even so, it sounds like a useful addition. If I'm a practitioner, when should I reach for this?
Reach for it when your task naturally decomposes, data cleaning that benefits from splitting and reconciling, content synthesis where you summarize sections and then reconcile overlaps, lightweight analytics where you count per segment and combine carefully. Anywhere you can say, let's do the parts well and then knit them together. You don't need exotic infrastructure, just a clear plan and prompts that reference earlier steps.
And if I'm time or cost constrained, is this always cheaper?
Not always. Compared to a single pass or a simple chain, a graph usually means more calls. The upside is higher reliability on tasks that benefit from decomposition. Versus tree of thoughts, though, the graph can be more cost-effective because aggregation and refinement reduce wasted branching. It's very task-dependent.
I keep thinking about that volume idea. Can you give a simple mental model?
Picture a river delta in reverse. At the mouth is your final answer. Upstream are many tributaries, intermediate thoughts. A chain is one skinny river. A tree has branches that never rejoin. A graph lets tributaries meet, so more useful water reaches the mouth. The trick is to route the flow so you carry signal, not silt.
Looking ahead, where does this line of work go?
3 directions stand out. First, automating the graph design so you don't rely on a person to sketch the plan. Second, pairing the graph with verification and external tools so merge and refine steps can check facts, not just style. Third, broader benchmarks that look like real workflows, longer documents, noisy inputs, conflicting sources, and a range of model families, to map out when graphs pay off and when a simple chain is enough.
If a team wants to try this next week, what's a good first experiment?
Start small with something you already find error-prone as a single pass, like reconciling 2 similar product lists. Sketch a plan, split each list, normalize items, match overlaps, merge, then run a brief repair loop where the model checks for duplicates or omissions. Keep prompts short and explicit. Track missing items, extras, and cost, and compare to your current baseline.
That's actionable. Before we wrap, can you remind listeners of the provenance?
The paper is titled Graph of Thoughts, Solving Elaborate Problems with Large Language Models. It appeared at AAAI in 2024. Lead author Maciej Besta and colleagues are primarily at ETH Zurich with collaborators from CLIDAR and Warsaw University of Technology. The authors shared code and prompts, though model updates over time can shift exact numbers.
So the bottom line?
If you've tried step-by-step or tree-style prompting and hit a ceiling, consider a graph. It lets you split, merge, and refine in a more natural way. The evidence on controlled tasks is encouraging, and the idea maps well to everyday workflows. It's not a silver bullet, but it's a solid addition to the prompting toolbox.
Clear and helpful. Thanks, Daniel, and thanks to everyone listening. This has been AI Podcast. Until next time, take care.